Hi, and welcome to this week's online topic where we're going to talk about determinants and transformations. So we're going to define and compute determinants, to distinguish between independent and dependents, and solve problems using linear transformation. So what are determinants? So recall that we talked about a matrix that is a 2x2 matrix where we have A, B, C, D. There is a formula for the inverse, which is where we take D and A and we flip our A and D, and then we put negative signs in front of the B and C. And this is multiplied by 1 over this determinant. So this is the determinant. Of course, AD minus BC cannot be equal to 0. Otherwise, it wouldn't make any sense. Now, for an m by n matrix, the submatrix is obtained by deleting the ith row and jth column. So, for example, to find the submatrix of A23, we would delete row 2 and column 3. And what's left over is that submatrix. So you see 1, 1, 2, 3, 0, negative 1, 1, 1, 1. Now, the definition for the determinant, if it's just a 1 by 1 matrix, so just one entry, it's not very interesting. It's that specific value. If the determinant is, if the matrix is a 2 by 2 matrix, then we have A11, A12, A21, and A22. We just cross multiply them. So it's A11 times A22 minus A12 times A21. So it's given by this formula, which is the same thing as we found back here. It's AD minus BC, and you could check this if you wanted to put, as we did before, A, B, C, D. This is just A times D minus B times C. Now, the determinant, if n is greater than 2, it's that coefficient comes out front times the determinant of that submatrix minus this coefficient times the determinant of that submatrix, and so on until you've exhausted it. I'll explain this in a second regarding this term, this -1 to the exponent 1 plus n. That is just, there's an alternating pattern, which I'll explain. But essentially, you take out the coefficient and compute the determinant, and then you move along to the next entry, take out that coefficient and compute that, the determinant of that submatrix, and so on. Then you sum them up, because a determinant is essentially, to relate it to what we've previously done, it's basically a number. It gives us essentially the magnitude in a way. So to compute this determinant, we would take out the 2 and compute the submatrix. So we take out the 2, and then we have determinant of -2, 0, 1, 2. Then we cross multiply it, -2 times 2, subtract 0 times 1, and we have this. This is -4 times 2. Let's color code that. The next one, we would remove 1 out front, and there's a pattern. There's a -1 that comes out. So -1 times the determinant of the submatrix, which is -3, 0, 2, 2. And then we cross multiply. -3 times 2, subtract 0 times 2. That's -6 times -1. This is +6. And then the last one is you take out -3, comes out front, times the determinant of that submatrix. So -3 times 1, subtract -2 times 2. which is here. This would be, make it a positive 4 plus -3 times -3. So this is 1 times -3, -3. And then you can compute it and get the final answer, which is -5. Now there's a link between determinants and vector cross products. Remember that I, j, and k, this is just those component vectors. So I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. If you calculate the determinant of a vector u and a vector v, where u is 1, u2, u3, and v is v1, v2, v3, we can write it like this. We would write it in this particular way. Take out the I in front times the determinant of this submatrix. You can also use, please notice that to the notation, the determinant can be written as these bars. So I'm just writing here, this is the determinant when I use like these bars. Then you cross it, and it will be basically the cross product. Here we take out the -j out front, and that a submatrix, the determinant of this, and so on. And if you compute this, this is actually the cross product like we did before. Now let A be a square matrix of order n. So we have a square matrix, order n. And let Aij denote a submatrix of order n-1. So it's removing a row in a column somewhere. So the order will be 1 less, obtained from removing that specific row and column, the ith row and jth column. Then the Ij major is just, it has a special name. It's called the determinant of that submatrix. And the Ij cofactor of A is the determinant of that submatrix multiplied by this coefficient of -1 to the exponent I plus j. I'll explain this in a second. It's just a factor, a coefficient. It just gives us the sign that goes in front. So the cofactor is the one with the sign. So find the 2,3 minor and 2,3 cofactor of this specific matrix. So the 2,3 minor of this determinant of A23, so deleting 2 and deleting 3, this is our submatrix. Okay. So we have so we can calculate the determinant of this. So again, we could go along this first row. So we'll do this. So 2 goes out front, and then I won't write this all out, but 0 times 0 minus 4 is where we get this. Then we bring out, it alternates. There's a negative, and then there's also a -2 due to the coefficient times 1 times 0, that's 0, minus 1 times 3. So there's a -3. And then the last one is positive. So that coefficient goes out front. And then we have that determinant of that submatrix. So 1 times 4 minus, that's going to be 0. So 4. And then we can calculate this and we get -10. Now the cofactor, this was the minor, it's just the determinant of the submatrix. The cofactor is the same thing. So this plus this term in front. So this term in front is -1. The exponent, it's I is 2 plus j is 3. So this is -1 to the exponent 5. It's odd, so it's -1. So we put a negative in front times -10. So our answer is 10. Now, what I was expanding essentially along the first row to calculate the determinant, we can actually expand along any row or any column. And let's see like the formula. So we can fix essentially a row, so the if row, and we can expand along that. So in order to do that, you would choose a row. So choose row, and then expand along that. So it will have a coefficient of -1, so the exponent I plus 1, times that coefficient times the determinant of that submatrix, plus the -1. Next one is -1 I plus 2 times that coefficient times the determinant of that submatrix, and so on. Then you sum them all up because the determinant is just a number, and you got that number. Or you could choose a column. And you can also do the same thing. So you have that -1 to the exponent I plus j, which I'll explain, times that coefficient, times that determinant of that submatrix, and so on. And then you move to the next entry and so on. And then you sum them all up. So it means that there's expansion along any row or column of a square matrix yields the determinant. So you could choose the rows and columns with the most zeros. It's your choice. So this coefficient, an easy way to look at it, it's positive, negatives, and so on. So positive, negative, negative. So you start with positive, then negative, positive, negative, and you find the entry corresponding. So the signs essentially alternate. So let's compute the determinant of this. You see that there's zeros in the second and fourth row, and the second and the third column, like 0, 0, 0, 0, like these zeros here I'm filling in. So we can choose which one essentially we're going to expand along. So we could use the fourth row. You could use the second row. There's nothing special. So this one is positive, negative, positive, negative. So this would be -5. This is positive, negative, positive. So -5 times the determinant of that submatrix. So this is why there's -5 times the determinant of that submatrix. Plus the next one, this is color coding it. So these are zeros, so we can ignore it, 0, 0, because those coefficients 0 times whatever that determinant of that submatrix is still going to be 0 because of the zeros. And then we can compute this one times the determinant of this submatrix. So that's this part here. Now we have to choose a row and column, but it looks quite clear that we have 0, 0, and 6 here. So we would want to go positive, negative, positive, negative. So we want a -6 comes out front times the determinant. I'm just going to use 2 bars to denote the determinant. 9, 3, -1, and 1. And we can compute this. 9 times 1, 9. Subtract 3 times -1, so that's 12. So this is 12. This is -6. This is times -5 plus the determinant of this one. Let's color code it again. We want to go positive, negative. So this is -4 times the determinant of this submatrix. So 9, 3, -1, 1. So this is -4 times same values that we got lucky there. And then we can compute this, which is done on the next side. So the value here ends up being 312 once we plug it all in. Now, to compute the determinant of this matrix, I recommend just kind of like pausing the video, and I will write out the solution. Now you can, before you do that, you can obviously go along the third column, but I'm going to just choose the first row and see how horrible it is. Or you could go yourself and try it at home. Here, the answer is -8, and you can check this yourself. So I'll just write this out. And I'm going to go along the first row and kind of torture myself. So do pause the video, try to do this yourself at home. Or try to go along the third column while I choose the long journey to the answer. And see which is easier for you. The long journey, which I'm doing, or the shorter journey. And just writing out the submatrix. Ran out of room here. So positive, negative, positive, negative. Okay, now we can compute. I kind of felt like leaving some zeros in because I figured it can sometimes be a little bit easier, sometimes. So 2 left and front. So maybe I'll write in a different color. Positive, negative, positive, negative. -1 times -2 times -1. This is 2. Subtract 2. So this becomes basically 0. Okay, the next one, -1 times, so positive, negative, positive, negative. So -1 again times 3 minus 4. This becomes -1, which is positive, which is negative. So this part becomes +1, this part, and then times the -1, so -1. The next part, there's only 1 0. So positive, negative, positive, negative, positive. So plus -3, just bring that down. 1 times, let's put brackets, 2 times -1, 2, minus 2. Next one is plus 2, this one, times -3 times 1, -3, plus 4. Okay, so this is 0. And this is 1 times 2, so this is 2. 2 times -3 is going to be our final. I'll write it in a second. Our last part, -1 times, and we have some zeros here, so this is positive, negative, positive, negative, positive. So times 1, so 3 times -3 times 1. Subtract -2 times 2, so +4. So this becomes positive 1, this because of this part. So 1 times 1, subtract 1. So let me write this out. So it becomes 0, subtract 1 times 1, subtract 3, that's a 1, times 1, -3 times 2, subtract 1 times 1 times 1. So this is -6, subtract 1, which is -8. Okay, so this was along expand along row 1. Now you at home can pause the video and try column 3 here yourself, and you should get the same answer. So if a square matrix has a 0 row or column, the determinant is equal to 0. If a square matrix has 2 equal rows or 2 equal columns, that determinant is equal to 0. And you could expand along the row or column to verify, but we won't do any proofs in this course. So to compute the determinant of B, for example, you see that 2132 is the same as 2132, so that determinant is equal to 0. Now recall that a square matrix is upper triangular if all the entries below the diagonal are 0. So this is an upper triangular matrix. A lower triangular matrix is of this form, which I mentioned before. If all the values above the main diagonal, so this is that main diagonal, are 0, and these are numbers. And a diagonal matrix is both upper and lower. So this one is upper, and this one is lower. I mentioned this before. Now, I was just reminding you. So if a matrix A of order n is upper triangular, lower triangular, or diagonal, then the determinant is essentially the product of all the entries on that main diagonal. So you could see this. Why? Because if we draw it out, let's just choose the upper one, and we have values here, 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 and numbers here, but these are all zeros. Then we would take out this first value, which is that coefficient or that number, A1, 1, and then we would compute that determinant of this submatrix. But then again, you take out this value, A2, 2, and you have the determinant of that submatrix, and so on until A(n)(n). So you could kind of visually see it. So to compute this determinant, we see that it's an upper triangular format. So we just compute the diagonal entries, which is 2, 1, 3, and -2, and get -12. So properties of determinants, our second section. So suppose we have 2 square matrices, A and A prime, and they are the same, except that in one row or in one column, A prime of A prime, each entry of A is a multiple of a scalar. So one specific row or column is a multiple, not the whole thing. So this C can be factored out of the row or column. So it does not mean that the determinant of CA is equal to C times the determinant of A. It just means one specific row can be factored out. So since CA is formed by multiplying every row of A by the scalar C, we actually have that the determinant of CA is equal to C to exponent n times the determinant of A. So if A is a 3 by 3 matrix, so our n in this case is 3, the determinant of 2A is equal to, we can take out the 2 to the exponent n is 3, times this determinant. So it's actually 8 times the determinant of A. And so you would see it sort of like this. You could just factor out the C, but it's each time. So it'd be C times C times C. So it'd be C to the exponent n if n in this case was a 3 by 3 matrix. So this is 3 in this particular case. So compute the determinant of A, given that we have like this matrix. So we could take out from here, where do we take out first? So we could take out the 2 and we could take out the 3. So that's why we have 2 and the 3. Then where should we take out? Well, we could take out here, this 3. So then we're left with -2 and 1, and then this becomes squared. Then we could see, obviously, there's a 2 here, which we could take out. So then this becomes 2, or sorry, this became 3 squared. This becomes 2 squared. Then what do we do? Okay, now we can compute this because it's 1s and 0s and 2s. So it makes it a little bit easier to actually compute. And you can compute this yourself and you get -72 times the coefficient, these coefficients. So if a square matrix A has a row that is a scalar multiple of another row, or a column that is a scalar multiple of another column, that determinant of A equals 0. If 2 rows or columns of a square matrix are interchanged, then the determinant changes by this factor of -1. So when we flip rows or columns, this factor of -1 comes out. If a scalar multiple of one row or column is added to another row or column of a square matrix, that determinant is unchanged. So this one is a little bit unusual property. So we'll see some examples. So compute the determinant of A of this matrix. Well, we could add, essentially, we might want to get rid of this A here. So we could add -A times row 1 plus row 2 to row 2. And then we would get 0. For the next one, it's -A times A, so that's -A squared plus 1. So we get 1 minus A squared. Next one's -A times -A, so that's A squared plus 0, so A squared. For this part, you would basically take row 1 times A plus row 3. Put it in row 3. Okay, so A times row 1, that's A minus A is 0. A times A is A squared plus 1 is 1 plus A squared. A plus times row 1, that's A squared plus A squared is 0. Okay, so we have some zeros. So now we can just take out the 1, and then we can cross multiply this part times this, which is here, that's 0, times A squared times 1 plus a squared. So this part is negative. There's a negative times this. So sometimes it's easier just to bring this to an upper triangular form, keep track of the row interchanges used, and the determinant is just then going to be the multiple of those diagonal entries. And so it's sometimes easier in terms of actual computations of keeping track of the interchanges and then just multiplying those diagonals. So let's find the determinant of this matrix. So we see it's almost in an upper triangular format. But there's a 1 and a 3 here, and a negative 1 there. So we might want to switch these, flip these. But if we do this, we have to keep track of the interchanges. So when we flip them here, we flip. These got flipped. A negative comes out front, because this is back to this property of 2 rows or columns are interchanged, then the determinant changes by like this factor. Counterintuitive. So, okay, so we have to flip it and we have to put a negative there. Now it's a little bit better. So now we can go ahead like normal. Once we do this, we have our negative out front that just comes from here because we flipped it. And then we can get rid of this 1. And it sounds reasonable. So we can take 1 minus 1, 0, 3 minus 2, 1, 4 minus 0, 4, 1 minus negative 2 is 3. And now we can do the same thing. We can get rid of this 1. We can just add row 2 plus row 4 is 0. 4 plus 1 is 5. 3 plus 0 is 3. Okay, so now we have negative 1 in front because of the flip, and we have it in an upper triangular matrix. So all we have to do, because we know how to compute the determinant of something like this, is just multiply those diagonal entries, because we would take out that coefficient and then have that submatrix, take out that coefficient and have that submatrix, and so on. So it's just those multiples of that diagonal. Negative 1 comes out front. I didn't write the 1 there. Negative 1, 2, and 11 over 2, and you get your answer of 11. So this is an important theorem. So a square matrix is invertible if and only if that determinant is not equal to 0. So you can only find the inverse. And remember, we're working with matrices. This inverse is basically how we divide using matrices, if and only if this determinant does not equal to 0. However, it doesn't tell us what this inverse actually looks like. We just know that it exists if it doesn't equal to 0. So is this matrix invertible? Yes, because the determinant is not equal to 0, it's equal to -8, therefore it's invertible. Let A be a square matrix, then the linear system AX equals B has a unique solution for every B, if and only if that determinant is not equal to 0. If A and B are square matrices of the same order, then the determinant of AB is equal to the determinant of A times the determinant of B. So we can take them out this way. If A is a square matrix, then the determinant of the transpose is equal to determinant of A. So Kramer's rules is our next section. So for a square matrix A, the classical adjoint of A is this submatrix with like these coefficients. We could call them C11, C12, C13, and there's just different ways. Sometimes they're called cofactors. C21, C22, 2, 3, sort of. C, 3, 1, C, 3, 2, C, 3, 3. And this is found by finding the determinant of the submatrix of Ji. So it's the jth cofactor times this coefficient -1 to the exponent I plus j. And remember, the matrix has to be square. So to find the adjoint of A, essentially we take C11 times -1 and this is our I, this is our j, determinant of that submatrix. You can compute this. This is 0, this is -4, and we get -4, and we put it here. Now, this is where it gets confusing. C12, this is I, this is j. So this is -1 to the exponent. 3, so this is -1. But the determinant of the submatrix, and I'll use a red color, this is 2, 1, this is 1, 2. So it's the determinant of the submatrix of Ji. So this becomes J and this becomes our I, essentially. And then we can compute that submatrix and get 5. Put it here. And the next one is 2, 3. So this is I, this is J. So the determinant of that submatrix, 3, 2, we can compute that, and then this is 0. So it's just be careful about the flip. There's another way of doing this where you just compute the determinant of 1, 2, the submatrix is 1, 2, and so on. So you just compute those cofactors, put them in the matrix, and then take the transpose, and that's the adjoint if you don't want to flip them at this step. I sometimes think that's more clear. Now, why do we do this? Because there's a simple, there's a formula essentially for the inverse. So the inverse is that adjoint that we found here by either flipping it in this step or taking another step and not flipping it and then taking the transpose. So, but if we just follow along, this is essentially the submatrix where the J and I flip, and these are, this is called the adjoint. And then we multiply it by 1 over the determinant of A, and this is that inverse of A. And given that A is invertible and not equal to 0, of course. Now, Cramer's rule, what is this? It helps solve problems of AX equals B. So denote Aij as the matrix obtained from A by replacing it, this specific value by B. It's easier to see an example. So let's say we have A and we have B. We take A and we replace A1. We take B 610 and replace it. And then for the second column, we replace it. And for the third column, we replace it. Now, Cramer's rule essentially gives us a formula for calculating and solving this. So it's the determinant of A1, which is over here, this one. So we calculate this determinant, and so on. And there's a formula for it. So it's divided by the determinant of A, the total. So let's see an example. Suppose we have like this linear system of equations, equation 1, equation 2, equation 3, and we put the info in our A and we calculate the determinant. It's not equal to 0, so it's invertible. Therefore, we know we can solve it using Cramer's rule. So we could calculate. So 1, 2, 3, we could put this 1, 2, 3, 1, 2, 3, 1, 2, 3 in A. Now we calculate the determinant of the top, the determinant of the entire A is 30, 30, 30, and then we have a solution for X, Y, and Z. And the next section is independence and dependence. So W is dependent if it's can be written as a linear combination of other vectors, where C1 and C2 are coefficients, and V1 and V2 are those vectors. A linear combination of like these vectors is this expression. So we can write C times V1 plus C2 times V2, and so on, Cn times Vn in this manner. So this vector, V1, 2, 3, can be written as a linear combination. V can be written as a coefficient, C1 times V1 plus C2 times V2 plus C3 times V3. And we can express this vector V as a linear combination of these vectors of -1, -1, and 3. But how do we find these coefficients? Now, let's see. So let's say we have like these vectors, V1, V2, V3. I express V3, so this is our V3, as a linear combination of the first vector, C1 times V1 plus C2 times V2. Well, what would we normally do? Well, we distribute the C1. So this would be -2 times C1 plus C2 for our first value. This is equal most likely to 4. Our next one is, this is 0, and this is negative C2. This is equal to -2. And our last one is C1 plus 2 times C2, and this is equal to 3. And you see from the second one, -2 is equal to negative C2, so C2 is equal to 2. And then you can just substitute this into whichever one you wish. So let's say the third one, so 3 equals C1 plus 2 times 2, this is 4, so the -1 equals C1. So we found our coefficients C1 and C2. So since V3 can be represented as a linear combination of the other two vectors, it is dependent on those. So let's make like this definition precise. So a set of vectors, so this is a set notation. Set notation in Rn is linearly independent if the only way to write the 0 vector as a linear combination of the other vectors is with all the coefficients being 0. That is the only solution to this vector equation. So if we can write this as 0 vector as a linear combination of the other vectors, it's said to be linearly independent. If the only solution is a trivial solution. So if all the coefficients are equal to 0, then it is said to be linearly independent. So all like these coefficients have to be equal to 0. So the only solution is the trivial solution. Therefore, then it becomes linearly independent. A set consisting of a single vector is linearly independent if that vector is not equal to 0. If the set is not linearly independent, it is said to be linearly dependent. So if you can write it as a linear combination of the other vectors, it is obviously like dependent, linearly dependent. If you can't, if the only solution is where the coefficients are equal to 0, then it's said to be linearly independent. So let's see. So determine whether this set of vectors is linearly independent or not. So we want to check this definition. So we could write essentially C1 times V1 plus C2 times V2 plus C3 times V3. Is this equal to the 0 vector? And like, are these C's, do they have a non-trivial solution or a trivial solution? So we could write this out and we could replace the vectors here with like V1, V2, V3, and this is equal to that 0. So in matrix form, we would see that this is 1. If we put C's along here, the C's, we see that this would be 1, 0, 1. When multiplying it out, would be this part here. 1, 0, 1 would be C1 plus C3 is equal to 0. and so on. Now, if this helps us, we can transform this into the augmented matrix. And then we see that the solutions to our C's are C1, C2, C3 are equal to 0. So therefore, these are linearly independent. How about to show that these are linearly dependent? Well, we could do the same idea and then show that these zeros are not zeros for like this question, or you could just try to rearrange and see. So this is like a set method, like this is kind of like a method that would help you do this. Or you could just rearrange and see that, well, and then set them to 0. And these coefficients are clearly not 0. Therefore, it's linearly dependent. So I'll leave that to you to check that. Suppose we have a set of vectors, and S is a linearly dependent set if and only if one of the vectors is a linear combination of the others. So to test for linear dependence, we construct a matrix A whose ith column of Aij consists of the components of Vi, and then the set S is linearly independent if and only if the row reduced echelon form of A contains only distinct elementary columns. An elementary vector has one component equal to 1 and rest to 0. So it's something like this: 1, 0, 0, 0 is an elementary vector. We call this E. It could also, the E, like let's say 2, could be something like 0, 1, 0, and the rest is zeros. A column of a matrix having this vector is called an elementary column. So we can also put these into columns. So let's see. So determine whether or not like the set is linearly independent. So we could, and you can see like sort of the connection between this formula, this is the same thing, and this. So essentially we put -1, 0, 2, and 1 in column format. And then we row reduced echelon form it. And you see that it is linearly dependent, because according to this, it's linearly independent if and only if the row reduced echelon form of A consists only of distinct elementary columns. Like we did back here, they had distinct elementary columns, and this was all equal to 0. Here it is not distinct. There's a row of zeros, so this is not distinct, so it's linearly independent or dependent. I will skip that. So our next section is linear transformation, section 5. So recall a function. So a function is a mapping from A to B. And it's essentially a mapping. It maps an element here to an element there. So it denotes from this domain A to this codomain or range B. There's a slight difference, but we won't get too technical. And for our purposes, we could say the sets A and B are vector spaces B and W. So we could call them B and W. I won't get into what a vector space is, but essentially it satisfies some properties. So if this ever comes up, like what is or was not a vector space, you can look up the properties and find these. So what is a transformation? So let's suppose B and W are vector spaces. So it satisfies like a list of properties. You can always search this if you wish. It's a bit more, the word vector spaces comes up frequently, but what is a vector space? It has these properties, and it kind of ties different types of math together. It ties matrices, it ties calculus, it ties rings and fields and different types of mathematics that don't seem like they relate, like calculus and matrices. It doesn't seem like it connects. It connects through vector spaces. It has like these special properties. So if it works for all vector spaces, then it would work for the same. And calculus, certain like continuous functions and calculus are vector spaces, then it would satisfy these in matrices, because matrices are also vector spaces. So it's this connection. So it helps connect to different mathematics together. So a linear transformation from V to W is a function from V to W. So it's just a transformation from V to W that satisfies like these conditions. Scalars factor out and it's additive. And again, vector spaces have some properties, and then there's also subspaces, but we're not getting too deep into this. So linear transformations are precisely the functions that preserve what is essential about vector spaces, mainly vector addition and scalar multiplication. So they preserve these properties. So there's, of course, the zero transformation. Like if you take a vector, like let's say U, and you transform it, you go to zero. There's the identity transformation. You take U and it maps itself to U. Very clear. There's this matrix. Let's say you have n by n matrix and you transform it and then you flip it and it's n by m. Well, this is, of course, the transpose transformation. So we gotta call it AT. So describe define this function. So we're going from R2 to R3, trying them the same as basically we have like this matrix A times this vector B. So find TV where V is equal to 2, 1. So all you do is essentially plug in 2, 1 into here and multiply it together and show that T is a linear transformation from R2 to R3. So we have A and we have B and we multiply them together. I will save you that, and we have 6, 3, 0. So we see though, like this vector here, this one is in R2, and this vector, the result, is in R3. So basically it took something that was in R2 to R3 by this multiplication. And we can also check the properties to see that indeed it is a transformation. So TU plus V, we multiply it when we do our transformations, AU plus V. And then we can distribute it. And this is the same as TU plus TV. So addition holds, and also scalar multiplication also holds. So it starts to give us like ideas in terms of, okay, the dimension, we just increase the dimension, but we can reduce the dimension and things like that. So linear transformations could be in a matrix. So suppose like we have AV, so this is our A and this is our B. And you could see if you multiply them out here by here, we're going to get like this matrix here. This matrix is in, this vector is in R3 or Rn, sorry, Rn, but it gives us a vector that is in Rm. So it changes the dimension of this. So we can increase the dimension, reduce the dimension, and so on. So consider the linear transformation. Find the dimension of Rn and Rm for like each of the following. So this is a 3 by 3. This is obviously a 3 by 2, and this is a 2 by 4. So if you multiply it by 3 by 1, because the 3 has to cancel, it goes from, so this matrix in our 3 by 3 goes from R3 to R3. this one would go from, this matrix 3 by 2 goes from 2, because it has to be a 2, to R3. This one here, it goes 2 by 4, so this would have to go from begin in R4 to multiply it out into R2. So you can kind of see like how it gets mapped to the next space. There's also rotations. I won't stress this. So linear transformations from R2 to R2, and you can also do R3, and you can rotate vectors, are represented by like this matrix. So cosine of the angle, minus sine of the angle, sine of the angle, cosine of the angle. And has the property that it rotates counterclockwise about the origin. So you have the origin, it rotates this way, rotates the vector. So let's say you want to rotate it 90 degrees across the vector, then we take a vector, put 90 in for your angle, and then multiply them together to get that transformation. There's also projections in R3. So let's say we want to project something. This vector would be a projection. And essentially, so if we take a vector in R3 and we multiply it by this, we will get x, y, and 0. So it's projected onto the xy plane, and this part is 0. So it's orthogonal projection in that xy plane. Now there's a standard matrix for a linear transformation. Suppose we're transforming from Rn to Rm, and it's a linear transformation such that we have like the standard basis. A standard basis would be like 1, 0, 0, 0, 0, 1, 0, 0. It's those basis vectors, those standard vectors. Now you can change actually the basis, but suppose here it's standard. So these elementary matrices, this transformation of the elementary, the first one is A11, A22, and so on. And these are the transformations. So we could actually put them into the matrix like this, and this is called the standard matrix of T. It's easier to see an example than theorem. So this is pretty easy. So find the standard matrix for the linear transformation from R3 to R2. So this is in R3, and this obviously is in R2. So find a matrix that converts this. So if we have a vector like x, y, and z, it takes this and converts it to this transformation and puts it in R2. So we could begin by finding the images of E1, E2, and 3. So in vector notation, you just put in our E1 is, and it doesn't 1, 0, 0. E2 is of course 0, 1, 0, and E3 is 0, 0, 1. And then we could substitute them in, and we get our values. 1, 2, -2, 1, and 0, 0. Or you could put it in matrix notation like this. Same answer. So we could take these essentially and make a matrix A out of it. So we just put them 1, 2, -2, 1, and 0, 0, and this is our A. So that's about it. So we could see that our A times our x, y, z is equal to that original value, which is equivalent. So we can put it in vector notation or matrix notation, and they're the same. So find the standard matrix for like this transformation. So we just basically, we have the transformation and we just extract those coefficients essentially. So 1, -2, 5, and then here we have 2, 0, 3, 4, 1, and -2. So we're just basically extracting that information, because you would see if you multiply x, y, and z, we would get this. So it's back to those equations. So it's the same concepts kind of repeated. So a reflection in the y-axis, remember, we have x, we have y, we have a point. So reflection would be over here. So this would be negative x, y. In the x-axis, similarity. This would be x, this would be y. Down here would be x again, but negative y. So this is why we have -1 here, -1 there. In this line, you could, of course, have the y equals x line. We have a point xy, then this would just be flipped, yx. So horizontal expansions and contractions. We could kind of like draw this, but if we have a point here, xy, then we could expand it kxy. This would be an expansion, horizontal expansion, and a contraction would be when k is smaller. Which I have another slide. A vertical would be, say we have a point xy. Vertical would be like x is held fixed times ky. And then we, of course, we could have a contraction as well. And then there's horizontal shears and vertical shears, which I left in the homework for you. So again, so when we have this y-axis, we take this matrix, and then the result is -xy. In the x-axis, it'd be x negative y, and a reflection would be yx, where they get flipped. So you can see when you multiply it by xy, a resulting vector. And again, there's the horizontal expansions and contractions. The result here would be kx, and the vertical one would be xky. Its expansion of k is greater than 1. The contraction of k is less than 1, but greater than 0. And then there's the shears. So it'd be like x plus ky. Y is just like a factor. It can shift over. You can see what that will look like. And there's other types of shears as well. This is just one particular shear.